Rather than use class time to go over the exam, I'm going to make videos where I show you solutions to the problems that students struggled the most on. So I'll post them on our XYZ homework by problem number. The first one I want to talk about is number 3, solving inequalities. And we talked about this early on. I gave you some exercises to do. It'll be really helpful for you later if you can master the technique. I don't think it's difficult, but it does take a little effort to learn it. And the key is to focus on these linear factors. Find where they change signs. They only change sign at one spot. And so because I have a product here, I want it to be positive. I can get that information by just analyzing the signs of the individual factors. So we draw a number line. We identify the sign change points. There's one at -5. That's where the first one changes sign, and another one at 3. So the signs will alternate. Like, I think we can have 2 regions here, and the signs will alternate as we move across them. If we knew the sign in one region, then we could just alternate. So one thing I like to do is if 0 is not a sign change point, and it's not, it will be on the next problem, I'll just plug it in real quick. And you can see when you plug in 0, you get 5 times 3. And I don't really care that it's 15, but I care that it's a positive number. So I'm going to put a plus in here. Signs will alternate. Therefore, this expression is positive only between -5 and 3. So here's our answer, the interval from -5 to 3. Open interval. All right, for the second one, the numerator changed sign at -1/3. You can set it equal to 0 and solve if you can't see it. At the bottom, we need a factor. We need to write it as a product of linear expressions. So I can factor that x out, and I get x plus 4 left over. And the sign change points are 0 there and -4. And now let's rearrange them on a number line. The smallest one is -4. We'll write it to the left. And then we have a -1/3. And then we have 0. So 0 is a sign change point. I can't use it to get the sign, but you can see easily if I plug in any positive number, let's plug in 1, everything is positive. So we're going to get a plus over here, and then the signs will just alternate. This inequality asks us for where the expression is negative. So we'll take everything less than -4. It is this region over here, and then we'll take everything inside here. -1/3 to 0, and we're done with problem 3. So the next problem I want to talk about is number 6, sketching the graph of a derivative given the graph of the function. So we're told here that the function consists its graph of a line segment and a quarter circle. Hopefully the pictures convey that. And we want to sketch a graph of the derivative. I should say that each section had a different version of this graph. All of them were a quarter circle and a line, but the details varied. So this is the one for the 12 o'clock section. So let's find our identified points A, B, and C. So start with the easy part, the line from B to C. The derivative of a linear function, as we know, as we talked about in class, is just the slope. You can see the slope of this line. It's negative. It's going downhill from left to right. We don't really know the value. There are no measurements given to us on the axis, so we don't really know the value. But we know it's negative, and we know it's a constant. So I'm going to draw the derivative for that part sort of like that. Some negative number, and it doesn't change. And at B and C, we can certainly B is a point of non-differentiability. The derivative doesn't exist, and C is an endpoint. We don't really care there. Now, the quarter circle, notice that all the slopes are positive. Over here at A, now that line I drew, it kind of messes it up. But if you imagine this is a circle, I'll show you down here. Then on these endpoints, the tangent line, the tangents are vertical. And we know that when, as the slope approaches vertical, it gets bigger and bigger. Okay, and we know that when there is a vertical tangent, the derivative doesn't actually exist. So we have a derivative as we approach A. The slopes are all positive and they increase actually without bound because we have a vertical tangent at the far side. So I'm going to sketch in an asymptote over here to help me draw that behavior. As we approach B, as we're moving around the circle like this, well, they could just keep getting flatter and flatter. In fact, at the very top of the circle, the tangent line is horizontal. So that has slope 0. So I'm going to circle in a point right here, and then the graph is going to do something like that, the graph of the derivative. So that conveys the information we know. I was really hopeful that the words here, the circle, we know what that means, vertical tangents at the ends, horizontal tangents at the top and bottom. That would help guide this. Now, it turns out I was pretty flexible in grading this. If you showed me a slope of 0 here and an increasing slope, maybe some people did something like this. They didn't quite realize that the slopes were approaching vertical as we approached that left-hand endpoint. But they knew they were getting steeper, so I gave that full credit as well. So let me go back to the right answer as best I can. Okay, so that's for the noon section. And like I said, the 8 o'clock and the 1 o'clock, it was just a variation. For some of you, the slope of the line was positive and the slope of the tangents on the circle were negative, but the concepts are the same. All right, that's number 6. Only worth 6 points, so it wasn't like a killer, but give you a chance to think creatively about the slopes.